we've got, the question is, what statement could one imagine making about sort of infinite metamathematics? So, for instance, here's a type of statement one can make. This was the kind of thing we were going for a couple of sessions ago, is this notion of constructive proofs being ones that were created by making models, where the proof follows from the proof follows just from knowing things about the model without you having to trace all the sort of all the individual pieces. And okay, so look, the big claim I was going to make at the very, very, very beginning of this was, the surprising thing about physics is that it's possible, as in, the surprising thing is that one can, that one doesn't have to follow every micro detail of the universe. One can make these global statements that come from relativity and quantum mechanics. And so the question is, in mathematics, what's the analogous statement? The analogous statement would be, you're not mired in, you don't have to go down, well, you're not mired in undecidability, which is probably related to, you don't have to go down to, I don't know how that's related to the question, but you have to go down to the sort of irreducible level of having to go sort of step by step by step, unable to use lemmas, so to speak. I mean, maybe the analog, what the heck is the analog? See, the claim would be that...
Well, can I take a quick crack? So,
yeah.
And I'm also getting pretty sleepy, so I'm probably not going to be really...
No, we should soon.
So from, like, I'm quite keen on the idea of coordinatization as like an important part of the puzzle. Mm-hmm. And in that picture, it would be, I guess the surprise is that mathematics is not riddled with singularities, like coordinate singularities, where you just can't say anything beyond a very short distance away. There's so much curvature that, like, your coordinates get scrambled and become meaningless, right?
Right.
But they're tracts that are useful, and that maybe that there's some scale involved, that you can zoom out a little bit and there's a coordinate change you can make, and suddenly you can talk about a new kind of more abstract object than before, and things continue to work at that new scale. Maybe that's my version of what you're saying.
Well, you're saying
that there is space, right? That there is some kind of the things limits to some kind of space in enough parts of mathematics that groups, for example, have examples that aren't just tautological. That you find groups in other parts of mathematics.
I see what you're saying. So you're saying that the fact that this thing could limit to a space rather than being full of singularities all over the place.
Well, the claim is that, like, for example, the idea of a group is a particular kind of coordinatization that shows up in all kinds of different axiom systems. In other words, there are models of groups all over other parts of mathematics.
Yeah.
And that phenomena of mathematics being able to describe itself is quite common. That if you look at one part of mathematics, you'll see other parts of mathematics in a sort of fractal-like way. And that is a claim about things not being so incredibly intricate and textured at any place in metamathematics that there's just no coordinatization there that lasts for very long.
Well, you're claiming that there's okay, so the claim would be there is a reasonably uniform coordinatization.
Or patches of them, right?
Okay, well, yeah, okay, right. Or patches in metamathematical space. And the implication of that you're drawing
is that, well, for example, there's computational reducibility. Right?
Sure.
That things like groups show up in other parts of mathematics, and they're not just vacuous descriptions of themselves, right? But you can apply them elsewhere.
So, I mean, my logic for all of this was the following thing. Okay, in physics, of all possible rule systems, there's underlying irreducibility. But the point is that the aspects of the behavior of those rules that we observe are ones that have been bucketed by the fact that we are computationally bounded. That is, we're not able to, we always create these equivalence classes and look only at the behavior with respect to the equivalence class, not at the behavior with respect to the very most underlying thing. And the speculation was that in mathematics, the way that we choose to do mathematics also does that kind of bucketing, probably through these extensionality axioms.
Footnote, because I don't know what extensionality axioms are, but yeah.
Okay. But I mean, they're just these axioms that say that they're like the univalence axiom and so on. They're axioms that say things that are equivalent can be treated as identical.
All right. So what's his face's identity of indiscernibles? Leibniz.
Is that right? I don't know that. Okay. Yes. Okay. That makes sense. Okay. I'm not surprised Leibniz was onto this particular thing. I need to look that up. I have this idea that the question is whether philosophers who said things that now seem obvious were saying things which were always obvious, but and that's why they're significant. What's that?
No,
Well,
we got
that's
lost
only
or
obvious
something.
now. I mean, there are plenty of things that look like computational irreducibility. I think is obvious now, but it wasn't obvious when I was first yakking about it. So it's so maybe I've got my own Okay. In any case, the
By the way, I do think it's a wonderful thing to think about, and I've enjoyed thinking about it a little bit. That like we all have our own, I guess, intuitions, and what are the things from the Greek geometers? We were just looking at him. Sorry,
Euclid
yeah, Euclid's whatever principles or whatever concept. What
postulates, common notions.
postulates, common notions? Yeah, so like we all have our different versions of that, and you can see, I guess, you can see those as some kind of coordinatization. And so things that are hard for things that seem obvious to you might have been completely alien to the previous generation of physicists or mathematicians or whatever. I mean, that's an obvious statement. But
No, it is. It's also, but it's an interesting statement because that's that's this whole issue about alien intelligences and their view of physics. Is what with different But my current logical thinking was that mathematics is doable because we implicitly assume certain axioms that cause us to bucket things in the same way, in the same kind of way that we bucket things in physics that lead us to things like relativity and quantum mechanics. So your basic point, okay, so I'm going to make a claim. Mathematics is in practice doable. And it's basically the same because you can reuse lemmas and so on that you've used before, that you don't have to reinvent everything every time you reach a new part of mathematics. You just can use a bunch of things you already knew to make progress there. Mm-hmm. Which is, I think, the same as, I mean, it could be the case that every new place you reach in mathematical space
demands its own unique coordinatization or set of lemmas or whatever.
Right.
With no relation to anything else, no intuition to go on. You can't do any parallel transport of your ideas from the spaces from which you came.
Right. So that is a statement that, mathematics is comparatively, so the reusing of lemmas you claim is a bit like parallel transport.
Perhaps, yeah.
Perhaps, not clear. But
but I mean, but there's an interesting point that, hold on, Stephen, but this connects back. I mean, there's a nice way of completing it back into your whole oeuvre, which is that that's just the parts of mathematics that we've had any ability to crack. So like people have just been scared off from all the shit that was just impenetrable forest, right? Mm-hmm. And that impenetrable forest is by definition computational irreducibility manifest, right?
Yes.
And so there's this, it's a silly kind of, the kind of argument where it's like, oh, we exist in a universe.
Yeah, anthropic argument, right.
It's an anthropic argument applied to mathematics, right? Like, of course, mathematics has been successful enterprise, and that's just definitionally so, right? The only puzzle is that any parts of it were reducible at all.
Well, I know, but that's the statement. I mean, that's the thing I've been claiming for ages. But the thing that I'm trying to understand now is it the case that, I mean, the thing that I didn't know 3 or 4 months ago, 6 months ago, whatever, is that physics avoids computational irreducibility. That the physics of the 20th century found a way to skate on top of irreducibility. That's the surprise. And so is mathematics also somehow skating on top of irreducibility?
How could those things come from a common place? Those seem to be, the clearing in the forest in both cases. How could that clearing derive from some fundamental principle? Isn't it just an anthropic fact, right?
No, I claim it is an anthropic fact, but I claim the reason it's an anthropic fact because we are computationally bounded. That the only thing you need to know, in other words, the logic is we are computationally bounded, implies we build a physics / a mathematics that we can do. Okay, now it might not be possible. It might be that we're computationally bounded and we're toast. It doesn't work. We can't figure out anything about what the universe is going to do or about what mathematics is going to do. But this fact that we can build, this might not be possible. But it is. And the claim is it is because of something to do with causal invariance.
Oh, okay, there's the payoff.
Right. So this might not be possible, but it is.